Hey everyone, let's take a look at this integral. We're going to use trig substitution to do this one. And notice that we have down here x squared plus what we would call a squared. And it's to the 3/2 power, so it's the square root of that and then cubed. But the a squared is 16, meaning a is 4. And since it's x squared plus a squared, our substitution is x equal a, which is in this case a is 4, times tangent theta, right? So you need to know which trig substitution to use. We've used x equal a sine theta, x equal a tangent theta, x equal a secant theta. So in this case, we need to use x equal a tangent theta. So first, I like to jump right away to my right triangle for this. In other words, I solve for tangent theta by dividing by 4. I get tangent theta is x over 4. So if I draw the right triangle, theta is the acute angle in this right triangle, or an acute angle in this right triangle. Tangent is the opposite over the adjacent. So the opposite side is x, the adjacent side is 4. And by the Pythagorean theorem, then the hypotenuse is the sum of the square of the hypotenuse is the sum of the squares of the other two sides. So x squared plus 4 squared, or 16, and then take the square root will give me the hypotenuse. Okay, and you can see in red, I've got a couple of expressions we'll come back to in a minute. So now let's see what this integral becomes in terms of theta. We know dx is equal to 4 secant squared theta d theta. So that's the dx. Of course, x squared is going to be 16 tangent squared theta. We'll have that. And then x squared plus 16 will be x squared, which is going to be 16 tangent squared theta plus 16. And to the 3/2 power, as I said a minute ago, is the square root of that stuff. And then we're going to cube it. Okay. So under the radical, I can factor out a 16. And then the product can be factored as the square root of 16, which is 4, times the square root of what's left, tangent squared theta plus 1. But by the Pythagorean identity, right? And of course, you have the help sheet with all the identities right here. We see that tangent squared theta plus 1, or 1 plus tangent squared theta, is secant squared theta. Okay. So then we take the square root of secant squared theta, and we get 4 times secant theta. Now all that's being cubed. 4 cubed is 64, and then secant cubed theta. So this is what we're going to replace the x squared plus 16 to the 3/2 power with, which is in the denominator. Okay, so x squared again is 16 tangent squared theta. Don't forget the dx. Dx is 4 secant squared theta d theta. And then, as we said, this stuff down here, x squared plus 16 to the 3/2 power, is 64 secant cubed theta. Let's simplify. Notice 16 times 4 is 64 divided by 64. So, I mean, all that can simplify down to 1, right? 64 divided by 64. And then I've got secant squared here, secant cubed. I can divide top and bottom by secant squared, and I get secant theta in the denominator. So I've got tangent squared up top, secant theta in the denominator. And this is what we're integrating now. I don't know any function automatically where this is the derivative. So let's see, how do we find the antiderivative of this? Well, there's a couple of ways we can go. We talked about doing integrals involving products of powers of secant and tangent. However, the secant power is negative, right? Because this is really secant to the -1, and the tangent power is even, which is not helpful. However, we just used an important trig identity. Tangent squared theta plus 1 is secant squared theta. Notice that tangent squared theta, therefore, is secant squared theta minus 1 if I subtract 1 from both sides of that equality. And that's when we use the Pythagorean identity to rewrite this as secant squared theta minus 1, all divided by secant theta. Now I'm going to divide each term by secant theta. So this becomes secant squared theta over secant theta minus 1 divided by secant theta. And the reason we do this now is, notice this is just secant theta, right? And 1 over secant theta, well, that's the reciprocal of secant theta, which is cosine theta. Hey, and we know the antiderivative of cosine theta. What about the antiderivative of secant theta? We derived that in class. That's the natural log absolute value of tangent theta plus secant theta. Antiderivative of cosine theta is sine theta. So here's our antiderivative in terms of theta. Okay, we want to get back to the original variable x, and so now we go back up to this right triangle that we have. Of course, we know tangent theta is x divided by 4. Secant theta, which is again the reciprocal of cosine, is the hypotenuse over the adjacent. Hypotenuse over the adjacent. Sine theta is opposite over the hypotenuse, x divided by the square root of x squared plus 16. So I'm going to replace tangent with x over 4, secant theta with the square root of x squared plus 16 over 4, and sine theta with x divided by the square root of x squared plus 16. Those are the values we just looked at. Now, if you get to this point right here, I'm pretty happy. This is pretty good. But if you look in the answers to this, this is not exactly the same. And so let me show you how we can get it to look like that. If I notice in here, I have a common denominator of 4, so I can add this as one fraction. It becomes x plus the square root of x squared plus 16 over 4. Okay, and then I'm going to use the property that the natural log of a divided by b is the natural log of a minus the natural log of b. So this becomes the natural log of the top, which is the absolute value of this stuff, minus the natural log of the absolute value of 4. Of course, 4 is just absolute value of 4 is just 4. So we just get the natural log of 4 and then minus all this stuff. Well, notice the natural log of 4, there's no variable here. This is a constant. This is some number, right? So the power on the base e needed to get 4. That's what this number is, and you can use your calculator and approximate that. But what we do then is realize, hey, if this is a constant and c is a constant, we can combine these together as one constant, and we're just going to call it c again, and it's just another constant. So in other words, this answer here that we got, this antiderivative, differs from this antiderivative here by a constant. Okay. So either form is acceptable. I'm fine again with this one. We talked about this one in class, or something similar to this rather. But if you look in the answer key, this is what you got. So that's why it's different from what you have there. Okay, so a lot going on in this one. You have the original problem. Get to the top here. You have the trig substitution, right triangle. Do all the transformations, including your dx, all right? Then you simplify the integral in terms of theta, you evaluate it, and then go back to the original variable x, again, using this relationship from our right triangle. So I hope this is helpful on this one.